Hi everyone, welcome to your impulse and momentum lecture. Sorry and bear with me as we go through if I need to pause, clear my throat, cough, etc. I'll do my best to edit any significant coughs out, but they might creep in there. But today's lecture builds on our previous day's lessons in regards to forces. And we'll start off with a little bit of a review, okay? So because this is video format, feel free to pause at any moment and then come back and hop in and see the answers and the work through. So first up, we have a question regarding force and net forces. So it's asking you to calculate the net force of this tug of war. And we'll see here that I associated some forces for each of these people that are pulling on the cart. The cart will, of course, be stopped to start with, but we can calculate where the net force is, okay? So I'll be 1 and 2. What would it mean if the sum of the net forces were to equal 0? So chances are for 1, you're going to get a non-zero answer. And then what would be the motion of the cart and collectively the people tugging of war, and what are the forces being applied, if any? So now is a good time to pause, and then I'll do the walkthrough, okay? So for question number 1, we take a look here. Really what we're doing is we're adding up all of these forces. Now recall that in this particular case, it's really important to remember that force is a vector, which means that it has directionality. So because of that, there's a number of different ways we can solve it. I'll just go through one way that I like to, and then you can. So for myself, I want to add up or sum all of one direction and then the other, and then I'll make my decision on directionality and then sum those forces. So if we look at, let's go with the blue, we see that we have 15 newtons, and this is the sum of force. We have 15 newtons plus 5 newtons. That, of course, is 20 newtons total. Then we can look at our red team, and we see the sum of the forces is equal to, I'll walk through it. 5 newtons plus 5 newtons plus 20 newtons, and of course that equals 30 newtons. Oh my goodness. Getting wild there with the newtons. Okay. But obviously these are in two different directions. So to find the net force of this scenario, I'm going to take my 30 newtons, and I'm just going to call that in the right direction, and I can just over top of that. But because the 20 newtons is in the opposite direction, I'm going to subtract those 20 newtons from that because that's in the opposite direction. And so at the end of the day, I have 10 newtons, and of course that's in that direction. Okay, so that would be how to calculate or sum forces. Okay, on the other question number 2, let's look at A. Okay, what do we see? Well, would there be motion if our F net equaled 0? Well, it's kind of hard to say what motion there would be if we didn't know the original cart's movement. Recall that from last lecture, a object will continue in motion unless acted upon by an external force, right? So if it was in motion and the net force was 0, we'd say that it was still in motion, but we can assume because it's a tug of war, the cart was not in motion before it started. If the force net was then 0, so both sides were equal and opposite in the force that they applied to the cart, there would not be any motion. So you can say no motion, in this instant. Wow, that was scribbly, sorry. And then B, are there forces being applied? Well, potentially. I mean, maybe it was before the tug of war and there's a net force of 0 being applied to the cart. And again, that would be a tension force through the rope. But assuming that both teams are pulling, as illustrated here, we can see both teams are probably, for the case of 2B, we're applying equal and opposite forces. Okay, great. Let's take a look at the next question here. So really it wants you to go through this diagram and identify the forces acting or related to the box. Okay, so we'll start with the one and then the ones related directly to the box, and then the forces acting on the box, and then those related to the box. And we'll be sure to state which object they are acting on. So again, it's really important and helpful to ensure when you're trying to go through identifying forces that you really define your object that the forces are acting on directly, okay? We'll see why. So there's a normal force, the gravitational force is involved. I'll have you in a moment pause and go through that. And B is what would happen if the identified forces if the box was flying through the air. So essentially, another way of saying is it's no longer in contact with the table. Hint, that means there's no longer contact forces, okay? So now would be a good time to pause, work through this on your own, see what you can identify. Okay, so assuming you had a chance to go through, here we are. So for A, let's get rid of that. So for A, identify the forces acting on or related to the box. Sorry, I'll just look here. So if we look at this diagram, we can see that our purple line is weight. Okay, so it's starting at the center of the box and being pulled towards the earth. So we'd label that weight. And even though it's related to the box, it is not acting on the box, it's acting on the earth. We can see that the earth is being pulled towards the box in an equal and opposite manner relative to the weight of the box, okay? Again, looking at the box here, we can see this yellow line or tan, trying to represent the same color as the table, is the table's normal force or contact force on the box, okay? The green line is the box's contact force in an equal and opposite manner on the table, but we'll notice that if we're only talking about forces on the box and we're only referring to the forces, again, directly affecting on the box, or if we were to draw a free body diagram of the forces applied to the box, we draw something like this. And so we have our box. Ooh, it's a little close to the top. And let's try to keep the colors the same. So we got weight. So the box's mass times the acceleration of gravity, and then equal and opposite to that, we have the contact force of the table pressing up on the box, and that's our normal force. Okay, so ultimately, this is what we're looking at for a free body diagram. The others are force pairs. They're not directly acting on the box. Remember, for a force pair, the partner force can't be directly on the same object. It has to be on a different object. Okay. So that's A. Now on for B. So what would happen to the identified forces if the box was flying through the air? Okay, so it's no longer in contact with the table. Well, essentially what would happen for B would be our normal force, or contact force, is no longer applied. And so it's just the force of gravity acting on its mass, so its weight. Okay, so that's that one. Now on to a little bit more calculating in regards to force and mass and acceleration. Okay, so I thought it'd be interesting vehicles are a great amalgamation of physics and engineering and obviously the properties that drive that. And so I thought it'd be a great example to take a look at a vehicle. So here we have a Tesla, and using some real numbers that I pulled in regards to that, we can see that this electric vehicle weighs about 2,000 kilograms. How much force is needed by the electric motors to accelerate to a speed of 10.3 meters per second squared. Now, you might think, wow, that's a really heavy vehicle. Well, yeah, battery packs are really, really heavy. And one of the goals for electric vehicles is to always try to be as light as possible, but they need enough energy for range. So it's always a bit of a trade-off. And that's why this goal for batteries anyways, for electric vehicles, is to get as energy dense a battery as possible. So more energy for less weight. And that'll lead to a more efficient power range. But this acceleration was pulled from real data. So out of curiosity, I went and found that the Tesla, one of the Tesla models, can go from 0 to 60 in 2.6 seconds. And knowing that its final velocity, and this is stuff we did last half, was 60 miles per hour, and that translates into 26.8 meters per second. Always got to go to SI units. And we know that acceleration period was 2.6 seconds. Well, we can take our change in velocity, which is 0 to 60 or 0 to 26.8 meters per second, and put that over the amount of time that change in velocity occurs, and that's our acceleration. So here we are, we calculated our acceleration. Okay. So again, returning to the question, how much force is needed by the motors to accelerate the vehicle? Okay. You can just assume one output motor, even though there's more than one. Okay. So you can pause now, work through that, see what you come up with. Okay. So let's work through it, assuming we've already paused and stuff. So here we are. We'll look at force times mass times acceleration. We'll look at the question, what do we know? What do we need to know? Well, again, we already know it's asking for force, but do we have the mass? Sure, it gave it to us. We got 2,000 kilograms. And what about acceleration? Well, went through and calculated that for you. So we have 10.3 meters per second squared. So if we want to find force, do we have everything we need? Absolutely. This is a great plug and play sort of question. So we got our force times mass. I won't put the kilograms, but I know it's there. 3, let's be proper. Kilograms per meters per second squared. There we go. And when we calculate those out, we get something around 22,600 newtons of force, okay? Now, depending on the electric vehicle and the make, usually what happens is you either have 2 separate electric drivetrains, so engines, sometimes even 4. Some electric vehicles have a engine per wheel. So again, depending on which model of Tesla and how it's engineered, we potentially could divide that and figure out what each engine's output is as well. But yeah, it was kind of cool. Real world, figuring out how things work and knowing exactly some inner workings and details about things like vehicles. Okay. So that's it for review. So again, that's setting our footing as far as forces are involved. So let's move forward and figure out how this relates to our next topic, which is momentum and impulse. So with this, I'll title it linear momentum or linear impulse, but at the end of the day, with linear kinetics, we're not going to be doing angular. So if we talk about momentum, talk about impulse, etc., it's all going to be linear. Okay, we'll get to some angular stuff a little bit later on. Okay, so what is momentum? Well, momentum is defined as the product of a system's mass or an object's mass multiplied by its velocity. So already it's kind of a bit of a straightforward concept in the sense that if something has momentum, it has mass, and it has velocity. That's it. Okay. Right, so how does that look here? Well, if we see that something's momentum is proportionate to its mass and velocity, we can call it it's the quantity of motion that an object has. Okay, but let's take some real numbers and see how that looks to some real world things. So we'll take a look here in the purple. I kind of outlined a couple of points. So just to try it out and guess, because lots of objects have mass and lots of objects have speed. In the real world, what's more tangible? What is potentially a bigger influence in our real world's understanding of momentum? Okay, so if we take a look here, our momentum, we're looking for at a football and a football player. Okay, so for our football, we are given that this football has a mass of 0.5 kilogram. Okay, we're going to multiply that by 30 meters per second, so it's velocity, right? And again, just as a reminder, I'm just getting this from our equation for momentum, which is mass times velocity equals momentum. So the P, or the rho sign, is momentum. And then, so we get that, and that is 15 the kilogram meters per second. Okay, so again, for the units, it's at the bottom of your slide, but also if you look at what's involved in this equation, it literally tells you what the units are going to be, right? Mass, which is kg, velocity. So literally right there, we got our equations in the unit essentially, okay? Or the units in the equation, and vice versa. Okay, so let's look at the momentum now of the football player. We'll go back to that. So we're being told that we have a 100 kilogram player, not unheard of, especially in the NFL, and that they can get going up to a speed of 4 meters per second. Now that's at the upper end, I think, of say like a sprint for someone in the combine, maybe a running back or something like that. So we do the math, and well, let's look here. We got 400 kilograms per meter seconds. Okay, so really, and there are quite a number of levels of magnitude larger that the mass of the player versus the football is, even though there's a 10-time larger magnitude in the velocity it's traveling relative the football relative to the player. We can see that obviously in this particular instance, in comparison, the mass of the player far exceeds the velocity or the mass of the football. Therefore, it has more momentum. Okay, so it has more quantity of motion, you could say. Okay. So the next concept we're going to explore is one of the conservation of momentum. Now, what that means is essentially when two objects collide, whatever amount of motion, so how much mass and velocity they had when they entered the collision, will be the same just after the collision. There's just a little transfer of velocity, okay? Because typically when two objects collide, they maintain their same mass, unless you're talking about planetoid bodies colliding and some of it remaining with one object versus the other. Typically masses stay the same for anything we'll be working with. So what we can do is we can look at this, okay? So we can set up an equation where and use just the velocity prior collision. So we set up something where in a pre-collision we have two objects, a nickel and a penny, and they have a certain amount of mass, right? They also have their respective velocities. So in this case, the penny has no velocity. So then the two objects collide. Maybe you slide the nickel into the penny, and afterwards they have differing velocities. Okay, the nickel still has some velocity. The penny has a lot more. Okay, well, how do we arrive at this? Well, and we can actually figure out exactly how much velocity either of these objects are going to have, because again, we know their masses and their velocities before and post collision are going to be equal to one another. We also know their masses, both at the pre-collision and post-collision, are going to be the same. So we know all those values. So we're essentially just solving for change in velocity between these objects. And sure enough, we plug it all in and kind of work through the math. We'll find that their, again, pre-collision mass and velocity is equal to post-collision. Okay? Okay. One other thing that comes from this is it helps give a deeper understanding and another way to look at Newton's second law. One of the ways that we can go about exploring that is, and again, I don't do too many derivations, and is if we start with this. Okay, let's try this out. Okay, so if we know Newton's second law most commonly as force equals mass times acceleration, right? But if we look at acceleration, we also know that acceleration equals a change in velocity over time. Okay, so if we plunk that into the equation, we then get something that looks like this: change of velocity over time. Okay. Now, something that we just learned from the previous slides, if we go back up there, from this equation, we know momentum is the same as saying mass times velocity, right? So if we know that momentum is mass times velocity, well, that's what we got with this term right here. So really what we're saying is that a net force acting on something is the same as the change in momentum over time, okay? So this is a really good placeholder and something to remember. So what are we saying? Well, something more or less, when it changes in its velocity, is having a net force applied on it. And the time at which that net force or change of velocity is being applied will change or demonstrate the amount of force being applied. So I'm going to say that and try to draw it again one more time for you. So again, what we're saying is if we change the momentum, which can also be written as momentum times mass times velocity final minus velocity initial. The reason we can do this, so that should be delta, is because we know the mass of objects typically stay the same, right? So knowing that, again, let's rewrite this whole thing just slightly different, just to see one more way to understand it. So momentum is equal to mass times something's final and initial, and that change over time. Okay? So again, if we're really trying to identify how, I feel like I did that wrong. Small momentum. My mistake. Okay. So if we're really trying to identify what changes the force, how can we figure out a force that's applied to an object, we can also look at the beginning and final velocities of an object and the time that it's applied. Because again, if we know the mass is fixed, these two variables will help us figure out the force. Yeah. Or how much force is needed to change the velocity for a certain amount of time, or how much time is needed to, so you can kind of rework those variables, right? So again, it's just a slightly different way to look at Newton's second law described in a slightly different way. All right, let's try applying some of that, okay? Again, so practice question, pause it, try to work through, I'll walk through it. Once you're done, or once I'm done the walkthrough, if you do or don't get it, well, obviously if you get it, you can move forward. If you don't, go ahead, rewatch it, and try to work through it one more time on your own, okay? But here we go. Okay, so in this practice question, we have Venus Williams hits a serve reaching a velocity of 209 kilometers an hour. This is a real serve that she's done in a tour before, or in a Grand Slam event. And so that converts, I figured it out, for 58 meters per second. So impressive. The athleticism, unreal. Okay, what is the net external force exerted on the tennis ball, you're given its mass, by her racket, assuming the ball's velocity just after impact is this final velocity speed, so that's her serve speed. What is the ball remain, like what if the ball remained in contact with the tennis racket for 0.005 seconds? So again, you see a tennis serve, it's really quick. The ball hits a racket and then continues on very, very quickly, right? Okay, so a hint for this one is there's 2 steps. You'll need to figure out information over two different calculations. Try to work through this, and then I'll do the walkthrough. Okay, here we are at the walkthrough. Great. So where do we start on this? Well, first off, we kind of look through this. Let's collect what we know, what we don't know, what it's asking, and we'll put that up over here. So we know for sure we have this velocity of it being hit or reaching a certain speed of 58 meters per second. That's the tennis ball, right? We know that's the top speed there. It very early on asks for the net force. Okay, so that's our unknown that we're trying to find. What other information? We know the mass of the tennis ball. Again, you can put tennis balls or T to keep track of things. You know, that's 0.57 kilograms. And last but not least, we're given time. That the racket is in contact with the ball. That's 0.005 seconds. Okay, so that's all the information we're given. Now we can start looking at our equations and seeing how can we figure this out, okay? Well, if we look at the Fnet equation provided to us, now let's go purple. There should be enough room. So Fnet. We see that that's equal to the change in momentum over time. We realize that we don't really know momentum or the change of momentum of this yet. Okay, so we need to go back and figure that out. So in order to figure that out, we look at our other 2 equations where we have momentum and change of momentum. Well, we know the mass of the tennis ball, so that'd work for both. And we know that there is a change in velocity, okay? So this is average velocity, this is change in velocity, but we know the ball is going to change in velocity over some amount of time. So I'm going to pick the second equation. So we have our change in momentum equals mass times V final minus V initial, and then we can start plugging in some terms. So again, the change in momentum is mass being 0.057. Oh my goodness, I'm just going to rewrite that. 7, that's kg. And then our change in velocity, well, we know the final velocity over here is 58 meters per second minus 0. And why do we know it's 0? Well, the ball is traveling on a vertical plane, and we're going to assume that we're wanting to know the calculation as the ball leaves horizontally. So as far as its horizontal speed or velocity, it's 0 until the racket hits and sends it in the direction that we want it to go. So initially 0. So when we calculate that out, we find that the change in momentum is 3.306, 3.3 kilogram per meter seconds, right? And again, just pulling the SI units from the equation itself, kilogram meters, minutes per second. Okay. So now we have more information that we need for the next part of the question, and we can carry that forward. So 3.3 divided by our time, which is 0.005 seconds, is kilogram meters per second. And once we calculate that out, we find that 661 newtons of force is being applied to the ball to get it moving at a speed of 58 meters per second. Yeah. Okay. Great. So moving forward on to the second part of our topic. So here we are, impulse, which is a change in momentum. A change in momentum equals average net external force multiplied by the time that force acts upon the object or the system. Okay. What's another way of saying that? Well, we were given this equation previously. We were just working with that. If we rearrange it, remember the kind of little triangle of the Deathly Hallows there, we can find that we've just restated what we already knew to give us the definition of impulse. Okay. Let's see how that looks. Okay. So if the mass of an object does not change, which it usually doesn't, we can use this and assume it to be true. Okay. So we can rewrite the change of momentum equals mass times the velocity final minus velocity initial, which we already used in the last equation, or the last question that we did. Okay. But yeah, ultimately impulse is noted with a large J or change of momentum. Now, the reason this is important is we can see that we can start figuring out some things by relating impulse and momentum, right? If we see that we have delta P or delta rho equaling force times the time that force is applied for as far as impulse, and we see that our momentum is mass times velocity, and again, the mass of an object typically doesn't change, what we arrive at is this, the impulse momentum theorem. Okay, so more or less what it says is we can increase or decrease the momentum of an object by applying an external force or by changing the time that force is applied for. And then we can change the velocity, change the velocity that an object experiences. So the amount of motion, the quantity of motion that an object has, right? Remember that was the definition. If we take a peek back here, the quantity of motion, that is momentum. So we change its momentum by changing its speed. Again, the object's mass typically stays the same. All right, this is all fine and great, right? You say, Tashant, but what does this actually mean? Well, in sports in particular, it's a great place to look at this. It means that if we want to change the velocity, say of an object, which is very typical, most sports have you wanting to either move your body or projectile, you want to get moving as fast as possible. All that says is to get this maximum amount of velocity changed, given the mass, we can increase, typically in sport, the amount of time that a force is acting on it. Okay? And usually a lot of technique or ways that sport is performed is trying to increase the amount of time, because the human body can only produce so much force. So how do you maximize that? Well, yeah, you can do training and increase the amount of force your muscles can produce, but you can also increase the amount of time, okay? Let's look at this in a slightly different context to sport. Oh, sorry, my example here in particular with, say, a baseball pitcher or a javelin thrower is you notice how long their strides are, right? Baseball pitcher steps as far down the mound as they can when they go to throw. They have a huge reach back, right? The javelin thrower and a huge step forward. So they're really maximizing their range of motion. Why are they doing this? Why have the most range of motion as possible? Well, the bigger range of motion you have, let's say longer stride, the more time you have throughout that range of motion to apply force to, say, the javelin or the baseball. And if you're increasing the amount of time, and we know that the mass stays the same, and your force kind of has that upper limit again, so the amount of force you're applying is fixed, the mass is fixed. If you increase time, you'll proportionately increase the change in velocity, okay? Okay. You can also decrease objects' velocity and therefore their force through a certain means as well. Let's look at this. It's a really good example. So if we look at this scenario, the person dropping off this stack of books, I think, you'll note that it's a fixed amount of height. So we know if someone or something is falling from a certain height, it's going to have a fixed velocity associated with it, right? Acceleration and gravity can only act on it for so long. It's a set amount. So in both scenarios, this person steps down, and we can say pretty safely that the change in velocity is going to be the same, okay? This person's mass is also going to be the same, right? Okay, so again, on the right side of the equation, we have our momentum equation, right? On the left, we have our impulse. Okay, so if our momentum is going to stay the same, how can we modify the force experienced by this person when they're dropping to be less? Okay, and sure enough, what we see is if we increase time, we can decrease the force, because the other side of the equation here has to stay the same, because nothing's changing over here. So if we have this force plate, which is what this is, and we notice when this person drops down with a locked out knee, what they're doing is they're hitting the force plate with all their force fairly quickly. So you see that big spike or a large amount of impulse over that amount of time, right? And the green line represents how long it takes for stabilization. So we can see a very short amount of time with quite a bit of force. Oh, sorry. Yeah, that's what that's depicting there. But when this person performs a soft landing, as they're about to do now, we notice that the time to stabilization takes a lot longer, but we don't see the same spike in force. Okay, so again, here, we're increasing time to decrease force. Okay, so here on the left side. Okay, so longer time, less force. So you could say the peak impulse of a soft landing is much lower. Okay, now obviously in this instant, for a very small fall, not too traumatic for the body, the human body. But let's take a look at an example where it definitely matters and is very important to slow down or to decrease the amount of force something experiences, okay? So if we look here at our parkour example, okay? So in parkour, the safety roll is often used to make landings from great heights or with great speeds, more physically manageable, right? So I was going to show a clip here, but some of it I don't. You can Google it if you want. But I've seen some people take some very large leaps, 10 meters high, and land on a pile of sand, and they do the safety roll off of it and kind of continue their momentum or distribute their momentum over time. Okay. So if, again, we're looking here, we can notice that we're going to have two comparisons. Okay. In one scenario, the person's going to land with very little time distribution of the force or the impact they land with. So their impulse is going to be have a very short amount of time. On the other situation, you're going to have more time. So they're going to perform a safety roll. That's essentially what this question is saying. Okay. So 5 meters up off a building, onto a pile of sand. They have a certain velocity and their mass. Okay. So again, go ahead, go through this question, try to figure that out for yourself, see what the difference is. You're going to have to calculate the two scenarios, and then we'll do a walkthrough together. Okay, assuming you pause to do that, at least give it a go. We'll look here, and right off the top, we'll see that we're looking at our impulse momentum equation. So we have force times time, change in time equals mass times velocity final minus velocity initial. And we can, of course, rearrange to get time over here because the question is asking force. What is the net force difference between these two scenarios? So we divide both sides by that. And up here in the gray, you can see that the sum of the forces net is equal to mass times velocity final minus velocity initial over time. Okay? So from there, what we'll do is plug and play with what we know. So let's see what we got. Should have done that first. Sorry, I got ahead of myself. I was just getting excited about highlighting some real forces here for you. So mass, we do know the person's 75 kg. They're going to stay that way for both scenarios. It also tells us that the height of the building is 5 meters. But do we need to know that? No. The helpful point of information from that is the velocity final, which we see is 10 meters per second. And then we have our two times. So we have time with, let's call it hard landing, and that, or maybe we don't know that. I'm getting ahead of myself. Let's say short and time long, okay? And the short amount of time is 0.1 seconds, and the long amount of time is a full 1.5 seconds. So that full safety roll, really drawing out the time relative to the other, okay? And again, as I mentioned, you just as I mentioned, you just plug and play. So we have the sum of force. In the one scenario, mass is 75 kg times our velocity final, which is 10 minus, or just at the top of the building before the free fall, 0 meters per second. I'm going to put that all over the time, so 0.1 seconds. And when we calculate that out, we see that we have 7,500 newtons of force. Okay, let's look at our second scenario. So let's say that was the short, this will be the long. Still 75 kilos, still 10 meters per second, minus 0 meters per second to start. And that's all going to be over 1.5 seconds. And we crunch those numbers, and what do we see? 500 newtons. So that's very, very significant as far as how many times less of a force our parkourers experience by doing a soft rolling landing by drawing out the time. To put this all in perspective, 7,500 newtons is equivalent to the weight of about 765 kilos. So if you can think of that force just literally laying on top of you, it's a huge amount of force that you experience in a matter of 0.1 of a second, right? I mean, once you start getting up to the magnitude of 400 newtons, that can break your femur bone, so the upper thigh, or a high elite mixed martial artist or Muay Thai fighter can kick up to 9,000 newtons, right? And again, these are applied over a very short amount of time. So when you start thinking about the forces that occur in the mixed martial arts or combative sports, they're very, very high, and it's amazing that the body can tolerate what it can. Later in the semester, as one of our final lectures, we'll explore just how the heck our body can withstand a lot of these forces and tolerate it and have our bones not break and muscles not tear, etc. Right? Okay. All right. So here's learning objectives. Final part are equations that we'll get to put onto our equation sheet. Again, you can use this to help guide your study. There will be a practice final that gets put out again as well to help guide your studies. Okay. Thanks so much. Hopefully, thanks for bearing with me there. And if you have questions, obviously you can email, and I'll do my best to answer them. Okay. Thanks so much, everyone. Hope you have a good day.